So my name is Shahbaz Baig, and I'm a PhD student at National University of Sciences and Technology. And I'm doing this PhD in collaboration with offshore monitoring company, a factory-based research and development company who is actually working with EU-funded projects for ocean navigation. And topic of my presentation is that we are actually developing a prototype or methodology to assimilate near real-time Earth observation data in multimodal Ensemble Kalman filter. So the background and motivation, which is actually also partially presented by Laura recently, and this I'm just building upon the same things. I mean, very real-time and latest knowledge of the physical state of the ocean is very essential to perform a very accurate and precise marine operations and in different applications. And current operational systems are dominated by altimeter drive geostrophic velocities and leaving a geostrophic contributions from wind-driven transport, tidal forcing, and coastal dynamics legally unconstrained by direct observations. And there are multiple platforms, Earth observation platforms, which can be used to drive the ocean currents, which can help us to drive the kinematic surface currents through different approaches, but yet their integration in ensemble-based data assimilation is not done yet very well. And this study demonstrates the operational feasibility of assimilating EO-derived surface currents using multimodal ensemble Kalman filter over glacial shelves in near real time. So this is just a study region because I'm not working in a global region for the moment to test this prototype. And this is the region where blue box is actually representing the domain of our research, and green shaded region is representing where we have the HF radar data, which is used for the validation of our results. So these are the list of the data sets which have been used in this study so far. The first one is the multi-sensor or multi-platform AVHRR data, which is actually providing sea surface temperature at 1.1 kilometers spatial resolution. While we have incorporated data enrichment strategy, so that by that we can achieve the temporal resolution of AVHRR data up to from 1 hour up to 24 hours. I mean, actually, depending upon our requirement, as fulfilling the requirements to generate or drive the ocean currents. And then we have the HF radar data, which is actually available with 5.5 kilometer spatial resolution, and there are 4 to 5 different models we have incorporated here. 2 are actually from the NEMO model, one representing the regional model and regional configuration model, and second one is the global. And along with that, we have incorporated HiCom with 8.8 kilometer resolution and GRTOS with the same spatial resolution as well. And we also utilize the NWS analysis data available from CMEMS to perform the extended validation of our approach. This is a framework architecture of our methodology, I mean, which depends, which actually started from the acquisition of data sets and preparing this data set for the assimilation, then satellite drive ocean currents estimation, then ensemble model generation from heterogeneous forecast models, as I just discussed in previous slide, and then implementing the actual multimodal ensemble Kalman filter, and then followed by the validation. So we actually utilize the well-known and almost well-matured model, which actually helps to drive the ocean currents from the sequential thermal imagery separated by different time lags. We have incorporated the time lag ranging from 1 hour up to 24 hours. And here in the left side, this figure is actually representing 2 figures or two satellite-based SST images at different timestamps. And while performing the template-based operations, we are succeeded to generate the displacement vector, and from these displacement vectors, we can achieve the ocean currents and velocity components. And here, in the MCC model, we have actually let me show you here. Okay, so this is the first at the top row is actually representing the first results from the MCC model, which is actually representing a very clustered and uneven based vectors representing the velocity vector, but definitely there is different noise based upon the maximum correlation. So we have applied the low pass filter to smooth it out and remove the noise and errors, and then we come up with such kind of results, applying the threshold of MCC, maximum correlation of different level, 0.6, 0.7, and 0.8, just to see which threshold is working well to remove the noise from the from MCC generated results. And these results are actually presenting the the results derived ocean current from the image pair, which are actually separated by 1.5 hours time lag. So while moving towards using these outputs, moving these outputs towards data assimilation or multimodal assemble Kalman filter, we actually perform the cycle-based data assimilation. I mean, we have divided the data set into 3 hourly timestamps, so that considering that if we have a data set at a particular time, we can just select the data from previous 2 hours and then in forward 4 hours to run the simulation cycle and generate update the output at that level. So this is just representing the trajectory for each respective timestamp. And after running the MCC over 1 hour, 1 month of acquired SST data from AVHRR, we have this level of distribution, temporal distribution of MCC derived currents. And on the right side, this is actually presenting where our MCC derived currents or vectors are more clustered with respect to our study region. So after running the simulation cycle, we generated this type of results while assimilating these MCC products into 4 different regional models which were discussed, and after performing some cleaning and resampling process. And these are results actually presenting at on same date at different timestamps. One is 10:16, second one is 10:36, and then 11:20. We tested this approach at different levels. The first level is once running the simulation each cycle while incorporating different EO products one by one, and then we see how the RMS is varying or improving with respect to the background and how the analyses are going towards. So here you can see the solid lines are actually presenting the RMSE over the background for each cycle. So I mean once and then black solid line is actually representing the final RMSE while completing the iteration of all to assimilate all the EO derived ocean currents. And the bars behind this chart is actually representing how many number of images or products have been assimilated to that specific cycle. And here you can also notice that for the background mean RMSE, we have around 0.8, and which has been improved up to a 0.5 RMSE meter per second for both UO and VO components of ocean currents. These are some illustrations while comparing the data, the generated or assimilated currents with HF radar data. And there are different regional constraints already we have observed, and the region during this season was not very much energetic. And as the EU drive results, our currents are actually more feasible to drive the mesoscale like features. So small features are not were not able to estimate. So that's why there are a little bit difference, and then there are some also errors exist in the HF radar data over the edges. So that's why we can also see some difference at the edges of the outer region. But overall, we have examined that MCC drive currents along with after the assimilation as well have followed the similar pattern, similar homogeneous patterns, but abrupt changes were not able to estimate. And then we also expanded our validation with while comparing this MENCAF assimilated results with reanalysis data. And here you can also see, and some reanalysis data is also showing that overall the region is actually showing us slow speed currents regions as compared to the assimilated results. So we can estimate that our results are actually overestimating with respect to the HF radar as well as some reanalysis results. We compare the results at different levels further. We see how the number of images or number of iterations play their role to improve the analysis RMSE, as well as how the spatial uh, uh, estimated currents also play their role so that we can build some settings how or what level of images should be considered to run the assimilation in future. So here you can see the best results. We have identified that if the images are between 7 to 12 um, uh, 12 numbers, and the spatial number of vectors are around 3200 to 3500, then we can achieve a better results as compared to if we go with very large number of images, just like a 41, or very large number of region of the vectors, just like 3700 to 4000. We are experiencing bad results. And there are a certain number of factors involved here. Increasing the number of images can incorporate redundancy, because we have not tested how the images with different time lag settings are coming up. Definitely there are they also have their own uncertainty based upon the time lag. In the past researchers in the past literature, such as mostly discussed that the time lag ranging from 3 hours to 24 hours provide a better drive ocean currents as compared to the less than 3 hour time lag. But we have actually tested this approach as well, because the limitation in the research was also not unavailability of the required data. So data enrichment strategies help us to also test the data set, test the approach for the for the time lag less than 3 hours. And then while performing the MCC and then performing some low pass filter, we have a large amount of data gaps also, which are not readily available from different due to cloud cover or other effects. So we fill these gaps with using the calm weather value, but this calm weather value can further improve through scientific approaches like PCA or other interpolation techniques, instead of just using the calm weather constant value, which can also further help us to improve our results up to a certain extent. And then we also perform the validation while computing the complex correlation phase offset. And here you can see, and most of the directional alignment is closer to each other. And the mean offset was achieved around 7.4 degree with respect to the reanalysis data. And while computing the scatter index, we have identified that about 65% of velocity vectors have been properly aligned with the depth average reanalysis data. So this is a summary. We have actually developed or tested the operational feasibility of assimilating EO-derived or SST-based ocean currents with an automated 3-hour cycling framework under realistic cloud cover conditions. And then central scientific findings is that assimilation scales governed by the spatial distribution and quality of Earth observations rather than volume alone, and actionable for operational observation strategy design. HF radar and as well as reanalysis based validation help us to achieve the RMSE around 0.18 meter per second, and scatter index is around 65%, and the results for which these metrics are computed are 175 cycles, which I have actually showed, and the overlaying with between both data sets. And the transferable sensitivity framework, and this is actually a performance characterization as a function of observation density, spatial coverage, and temporal sampling. So this is applicable beyond the present regional configuration and observation type. We can incorporate different data sets. We can expand this, test this approach at different regions while utilizing the similar settings. The future work is that we are aiming to implement the scientific gap filling approach instead of using the calm weather value. And then we are also we are aiming to improve the observation selection strategy, just like I just represented that we have selected 2 hours back and 4 hours forward to select the observation to perform a simulation, but we have not tested which time lapse settings are performing well and which is not. So based upon that, we can further improve this approach. Then ingestion of multi-sensor data, other than multispectral or sensor data, we can also include the SAR-based data so that we can get rid of the issue from the cloud cover region. And this because researchers are also implemented the MCC algorithm to drive the ocean currents from the SAR data with a good agreement. So we are aiming to implement as a fallback option from the different sensor data. Then expanding the evaluation over multi-year and multi-season so that we can see the robustness of this approach. And then finally, we are also interested to incorporate the machine learning models to perform the Assemble weightings during the Ensemble multimodal Assemble Kalman filter implementation, as well as predicting the background error of our selected models. So that's all.
Yeah, thank you.
Thank you.
So yeah, feel free to write questions in the Yopad document. I've got a question from Lars Nerger, who is asking, what was the motivation to run the Ensemble Kalman filter in a multi-model setup in this domain, given that also the effort to configure such regional model setups? Shouldn't a single model with stochastic perturbations in the model physics be sufficient?
First motivation was using the different model outputs instead of setting up one single model. I mean, the different models have their own structure uncertainty. So this helps us to determine or incorporate the uncertainty from different models instead of just running or setting up one single model and changing the initialization to generate the ensembles. So one was that, and second is the main. We would not I don't have such access to this type of regional models, and there were also other limitations as this. So instead of setting up one single model, because we, as I said, that we are working in collaboration with the research and development company who is actually using these models from different sources. So we were more interested, instead of performing some weighted average or weighted analysis to get the best model from all these available well-known products, so get the best one. So building upon that, we decided let's get all these publicly available models and improve them with the EU data sets.
Yeah, so this sort of makes me think of a question. It might betray a lack of understanding on my part, but if you've got all these different models and you're running an Ensemble Kalman filter and you get some increments, how are you, if the models are very different, how are you applying those increments? Are you applying them to all of the different models?
Well, actually, we are actually, let me show you here. So what we are doing, we are getting or acquiring all these different models from different sources, and we are actually improving them with respect to the availability of data sets. So just an example, if we are at this timestamp and we have at this timestamp we have a certain amount of data sets from the Earth observation satellites. So we are actually driving these ocean currents and improving this specific timestamp up to a short time forecast indirectly with respect to the how much number of images we have in future. So we are not improving incorporating the increment of the forecast model itself.
I see. Okay, maybe I should ask you more about this afterwards. I probably it wouldn't be fair not to ask Jenny Waters' question. So I was gonna ask. So she's asked, have you considered using an OSSE approach to study the impact of assimilating the MCC-derived currents? And also, do you have to take care about inertial oscillations because of the times of the observations and the model feels? Oh, she's still typing, but you get the idea. So do you have to worry about inertial oscillations?
No, actually, this study is actually based upon on the foundation of the MCC. MCC was tested by my co-author for the SAR data as well. So our aim is towards moving towards the near real-time data sets assimilation, or building an approach which can help us to assimilate or improve the ocean forecast products at near real-time domain. So we have not tested the other approach so far. And secondly, I don't know what is inertial oscillations, etc. Things maybe I have to further explore them, and will try them.
Okay, thank you very much.